also thanks for
giving us the opportunity to do this.
And second, like Fred said, this is actually a shared talk between myself and Cameron, but because of the logistics, we'll be doing the whole thing. But again, Cameron is the second speaker on this. I want to briefly introduce the Google Sparse Compilation. Full screen here.
Is this better?
Better, yes.
Okay. Sorry about that. So this is the Google Sparse Compilation, so that's when you see like patches coming in
CT continuous.
This is work like MLIR compilation explains the compiler Three slides, which is of course pretty compiler is always why we need to take the tensor Sparse. Typically, we want to reduce storage requirements. Now, this can be very memory hungry. By using Sparse, we can reduce that hunger quite a bit. Because of the reduced computational time,
Let me check
adding 0 or multiplying by 0. One quick note is that it's really a mathematical property, not so much a numerical property, because if you have things like multiplying with mathematical, things like that, triple is a very different standard here. And for the moment, that sometimes it does matter. Anytime we're talking about exploiting sparsity, there are certain issues that okay, we think about it as math and not so much as numerical properties. And lastly, you make a distinction between general sparse, or also total structures, or structured sparse, where you can think about structured sparse as having like geometrical properties, you have bands or blocks, things like that. But structured sparsity can also be like invisible to normal eye. You can think about 2 out of 4 sparsity, something that some GPUs or GPUs can accelerate. And actually, if you put 2 out of 4 sparsity is like the left-hand side. So you would think it's like an unstructured one, but it is actually a hidden structure that assemblers can exploit. But they're not so obvious when you actually print them. Well, we all know that dealing with sparsity explicitly is costly. Maintaining the code is like error-prone, it's complex, and especially in ML, like ML frameworks have like very limited support for sparse storage schemes. Sometimes they have like a CSR, sometimes they have a CEO, things like that. But they only have very limited operations on those data structures. And what is typically happening is that people use like custom operations. So they extend the ML framework with like custom operations, and then they can exploit sparsity. But of course, it's a very limited and very cumbersome way of dealing with sparsity. So, as we all know in this workshop, we believe in the implicit sparsity. So we think sparsity should be a property or a type, and not a tedious implementation detail. And a sparse compiler should completely like generate all sparse code completely automatically from a sparsity agnostic. Think about it as a dense definition. And especially in ML, that is very nice because you can keep the whole front end, all the intermediate things that have been developed in that context, and just add a sparse type, and then you get the completely orthogonal explosion of like. You don't have to operation for every sparse tensor type. So this idea is finally long back from linear algebra. That was the first to formalize this to tensors, and in 2021 we started to incorporate this idea in MLIR. So there is a compiler infrastructure, it's not a compiler, but obviously there are like end-to-end solutions even with MLIR available even in the open source already. But the goal for Google was to use MLIR for an actual production compiler. very quickly the difference between approaches, and again, this workshop is all about this, so it's again preaching to the choir, but with explicit sparsity, like the programmer, the user, the ML expert, they like choose a sparse format beforehand, but then they're stuck with it. So the code has been completely rewritten for just that format. Think about it, you pick a CSR, you change your code, and then you measure the performance. But then, if it turns out that you actually made a mistake, maybe you wanted like have a CSC, you have to completely start from scratch again. With implicit sparsity, that is no longer the case. The code is completely agnostic of sparsity, so you just focus on the model, on the algorithm, whatever it is. And yes, the user gives sort of a hint for the sparse formats with simple annotations, but then the compiler generates it. And the nice thing is that when you actually made a mistake in the design, you can just go back and change the type, and then with the push of a button, the next algorithm, the next implementation of the algorithm is generated. And no design time is wasted by changing your decisions there. And what is even nice about this is that you can actually explore the complete state space exhaustively if you have time for that. So think about you have a model and you know you're going to run this many times. So you can afford to beforehand like explore a little bit all possibilities. So you can just generate all possible sparse storage keys and test it with representative tensors, and then you just pick the one that performs best, and then you use that in a production state. And you can even use like an L for an L, as you call it. So you use like an ML model that actually predicts how it will perform, and it finds like a In MLIR, we added what we call the taco-flavored annotation, if you forgive the pun here, but it allows for all the storage schemes that are common from CSO, CSR, double CSR, CSC, block version, ELL, but they're all in the sparse tensor type. So you see above the dense matrix multiplication in linalp, which is one of the dialects of MLIR. So you just say, okay, I have a 10 by 20 tensor and I multiply it with a 20 by 30 and the result is 10 by 30, just your vanilla matmul. The only thing that you have to do to make this a sparse matrix multiplication is change the types of one of the tensors. So here we say that OA is a CSC, and suddenly this becomes like an SPMM. If I had also changed like the tensor type of B, it becomes an SPM, SPM. And I can also say C, the output is dense or sparse. So you can see by just annotating with CSC, I already get many versions of the same operation. But if I then also change like the data structures, I use a CSR, I use a CO, you get this combinatorial explosion of possibilities, but I still use the linalp matmul. Like if we had introduced like the custom ops I was talking about before, that are used a lot like in the XLA compiler, you would have to generate one operation for every possibility. But by just completely keeping the type and operation orthogonal, you avoid this explosion of operations, but you still keep the power of letting MLIR generate all those possibilities for you. So this is our vision for the future. So we're thinking of all kinds of ML frameworks feeding into the compiler framework. So think about JAX, think about TensorFlow, PyTorch, PyTarco is already there. So that is what is like at the front end. But then they all feed into one intermediate. And the intermediate that will be used at Google in the OpenXLA context will be stable HLO. And we proposed adding sparsity to stable HLO. So think about stable HLO as just a representation at a high level. So I showed you linalp as a dialect. It will be an even higher level dialect, but it will have things like matmul, match factor, or maybe a general dot product, and you can add sparse tensor types to it. So everyone will be generating the same intermediate with sparsity, and all frameworks will support that one intermediate, and then everyone can like build their compilers on top of, or actually underneath it. So by having this shared intermediate, we hope that in the future, like all that effort of rewriting compilers for new frameworks will be a little bit reduced by using this one intermediate. Then we'll have the OpenXLA compiler, and as part of it, we'll have the XLA sparse compiler, which will be the MLIR-based sparse compiler pipeline. But again, MLIR is an infrastructure, so anyone can use it to build their own compilers. And we really hope that, like others, are encouraged to contribute or use some parts of MLIR. We don't want to be like competing with other solutions. We don't want to say, oh, okay, we are faster than MLIR. We would like people to actually contribute to MLIR so that everyone benefits from the open source nature of this infrastructure. And then at the very bottom, we have like all our targets. And I kind of simplify by saying CPU, GPU, TPU, but you can also, of course, think of the mobile versus server market and things like that. ARM versus Intel, there's many other components there. But this is a little bit like our vision towards a very healthy sparse ecosystem. So we have frameworks on top that have sparsity. We have an intermediate with sparse tensor types. We have a compiler infrastructure, people build their compilers with it. And then we have like a lower level targets that we can support. So I was going to talk about how to bring MLIR into production. So we chose SparseJax as our first framework to implement. And the reason is that it's almost a perfect match but like the MLIR sparse compiler. So a very brief introduction to SparseJax. I hope that everyone knows JAX. It's really like an ML framework that is based on NumPy but a little bit higher, so hence the JNP rather than the NP alone, because it's the JAX NP. It supports like transformations such as batching, jitting, but also taking the gradient of code. That's all the stuff that you like from an ML framework, JAX. But then SparseJax extends that to allow for sparse data structures. So if you have this function foo, which just takes x and then it says, okay, take a dot product of x. So that can be anywhere from like matrices to tensors, or sorry, from vectors, matrices, and tensors generalization. And they are typically in JAX used for sparse. So here I just take a vector, I say, okay, construct this vector and call foo, and then you get the dense version of foo. But if you change the operand to a sparse data structure, and in SparseJax that's called BCO. So you see that I take the data indices, it's a little bit like a CEO format, but it's batched, so hence the BCO. And I call the same foo method, then suddenly I get the sparse version of foo. So this is exactly the sparse compilation that we all in this group love so much. So you have exactly the same code, but it suddenly becomes sparse. And this is why we chose like SparseJax as our first production vehicle. So we have a whole collab available for this. So you can just type like JAX code, but then you have a decorator on a function, and you say sparsejit. So this will like generate sparse code when necessary. So you can still call this foo, of course, with dense ones, and then it will just jit as before. But the moment you call it with like a sparse data structure, so vec BCO in this case, a vector, sparse vector, then you see that it actually has computed the results and it operated on BCO. So again, you can use dense, you can use sparse. So the nice thing about Colabs is that you can actually embed like graphs with the code itself, and it's very interactive and very intuitive. So for example, an experiment like shown here is very easy to set up. You just say, okay, I'm going to like run a matrix multiply dense and sparse, and I plot the results out. So, and we use BCO here. So that's not the most efficient one. Typically you would use a BCSR for this, and it performs a lot better, but just for illustration purposes. So we plot the graph here. So from left to right, it becomes denser. So on the left-hand side, it's completely sparse. On the right-hand side, it's completely dense. And it shows runtime, so lower is better. And you see the blue line is just dense multiplication. Dense multiplication is completely agnostic to whether there are zeros or not. The performance is constant. But obviously the yellow line is now our sparse generated code, and it goes from like really fast when it's completely sparse to a crossover point where it actually like matches the dense performance, and then it becomes slower as expected. It dips off a little bit, which surprised us too. We think there's some weird gas effects going on there, so don't focus too much on that. But it's very nice to see here that about like at 20% have a crossover between dense and sparse. Here's also, Paming did this really nice, cool demo. We can like express 2D convolution with the Colab very quickly. You just code it as if it's a dense problem, but then you can actually, like here it runs an edge detection convolution, and on a picture with about 13% non-zeros, and we get like 2.5 speed up. And again, this is just out of the box. Like there's no, like you just annotate it as sparse, that's it. The compiler does the rest for you. We're working on GPU code generation too, because the Google fleet has a lot of GPUs, so we want to exploit those too. We're sort of exploring generating CUDA code directly ourselves, but we think that NVIDIA is a little bit smarter than we are right now, so we also use like the libraries cuSparse and cuSparse Lite for 2 out of 4 sparsity and block sparsity, and we see how much performance we can gain from that, and we'll report numbers on that pretty soon. So we envision this hybrid execution in the future where you take this map null and you have a sparse JIT on it, and when it's actually a general sparse, no structure, we run it on CPU, but when we detect certain properties that we can actually accelerate, like a block sparse in this case, it runs on the GPU. And then sometimes in the future, we want to, of course, since it's the XDA compiler, we want to incorporate this also in our TPU backend. Very quickly, inside the sparse JIT, so some of the production plumbing that you encounter when you actually write a real compiler. So obviously we had to let the runtime of JAX talk to the MLIR backend, and we wanted to have like very minimum overhead. So sparse JAX has this BCO, so you have like the indices in the data packed in memory, and we have like a pack and an unpack operation to make this like the MLIR format, and then we annotate MLIR as being a CEO format, and we want to have a zero cost overhead. So here you see the pack. We really take the data and the indices, and then we have on the MLIR side the sparse tensor compressed singleton, so that's a CEO, and the positions, coordinates, and values are mapping one-on-one. So you don't have to copy anything from the NumPy world, the JNP world, into MLIR. So there's zero cost overhead. And unpack is when you have sparse output. You want to actually copy the results computed by MLIR back. But again, MLIR cannot like allocate data, so everything has to happen in JAX world. So JAX passes a buffer that is large enough, and then MLIR fills it with the result, and then we actually truncate it back in the end, so that you only have the number of non-zeros in your result. But these are like very quickly like the kind of issues you have to deal with. MLIR is a compiler infrastructure, and JAX is a runtime. So they don't always talk that nicely with each other, but you want to have like very low overhead parameter passing between the mechanisms. So I talked about that JAX is actually has all those transformations. So batching is one of them, but that fits really the Taco format very well, because the batch dimension is just the dense outermost dimension. So a batched CEO becomes like a 3D tensor in MLIR land. So the compressed singleton is just the CEO, but the batch dimension is the dense one. So again, we have this like order one copying or non-copying, like parameter passing without any overhead between the two, by just using like the beauty of the Taco formalism. So this was very quick, a little bit of the status we're in right now with MLIR. So we believe a sparse compiler should generate sparse code, but I think the whole audience here believes that. SparseJax was one of the ML frameworks that fit that philosophy really well. We have a very simple setup with a Colab that enable our ML developers to very quickly experiment with sparsity. We're working on GPU CUDA code generation, and we're working on structured sparsity because CPU does really well on unstructured, but GPU does a lot worse on that. So we're looking at block sparsity, 2 out of 4 sparsity, and the overall theme here in the banner is that sparsity should be a property and not a detail, not an implementation detail that ML experts have to deal with. Okay, that's my presentation. So, not sure, do I stay online for questions or do I break out now?